So far we discussed in amplitude modulation. Generally amplitude modulation is a linear kind of modulation. Also we have in our previous few classes we have discussed like some functional blocks like phase lock loop. Then we have discussed super heterodyne receiver and its relative merit, demerits, etc. Now we are going to discuss a kind of modulation that is nonlinear in nature, and that is called the angle modulation. In this kind of modulation, the angle of the carrier is varied according to the baseband signal. Generally, for this type of modulation, the bandwidth requirement is much larger compared to the previously discussed kind of modulations. And because of this larger bandwidth requirement, this angle modulation is also called exponential modulation. Exponential modulation. This exponential modulation inherently provides increased signal to noise ratio without increased transmitted power. So that's the biggest advantage of this angle modulation. So angle modulation may be defined as a process in which the total phase angle of a carrier wave is varied in accordance with the instantaneous value of the modulating signal while keeping the amplitude of the carrier constant. Now assume that the carrier is this. Where A is the amplitude, omega c is the frequency, angular frequency, and theta 0 is the phase angle. That can be written as A cos, say, phi, where phi is the total phase angle. Now in exponential notation, it can be written as A e to the power j phi. So if I want to get back our original signal, we have to take the real part of A to the power j phi, and that will give us this A cos omega ct plus theta 0. Now this phasor, this is the phasor notation. This phasor c rotates at a constant angular velocity of omega c. C rotates at a constant angular velocity omega c. Now phi is equal to omega ct plus theta 0 if we differentiate with respect to time. Then we can write d phi dt equal to omega c. And this is very important. For an unmodulated carrier, d phi dt is constant, right? But in general, this may vary with time. Therefore, the angular velocity of the phasor c would also vary with time. This time-dependent angular velocity or angular frequency is known as instantaneous angular frequency. Instantaneous angular frequency, which can be written as omega I. So omega I actually the differentiation of instantaneous phase. Now if I want to calculate phi, we can write it in this way, omega I dt. So that's the relationship that we have to remember every time. Instantaneous frequency and corresponding phi. So they are related to each other in this way. Now we can vary this phase angle phi in two ways: by changing the phase or by changing the frequency. So depending on that, we have two type of angle modulation. One is phase modulation, another is frequency modulation. So first let us consider the phase modulation. Well, phase modulation is that type of angular modulation or angle modulation in which the phase angle phi is varied. Phi is varied linearly with the baseband signal. Varied linearly with baseband. That means in phase modulation, the instantaneous value of the phase angle is equal to the phase angle of the unmodulated carrier plus a time varying component which is proportional to the modulating signal. So carrier signal a cos omega ct plus theta 0, that is equal to a cos phi, where phi equal to omega ct plus theta 0. If we neglect this term theta 0, phi approximately omega c t. Now according to phase modulation, this phase angle phi is varied linearly with baseband signal. So we can write instantaneous phase phi I equal to omega c t plus some constant into message signal m. This constant is the phase sensitivity. So phase modulated signal, so phi I equal to omega ct plus kp into mt. Kp is the phase sensitivity. So phase modulated signal st can be written as a cos phi I, that is equal to a cos omega ct plus kp into nt. Now consider frequency modulation. Frequency modulation is that type of angle modulation in which the instantaneous frequency omega I is varied linearly with a baseband signal. We have assumed baseband signal as mt. So omega I must vary according to baseband signal mt about an unmodulated carrier of frequency omega c. That means the instantaneous value of the angular frequency omega I will be equal to the carrier frequency omega c plus a time varying component proportional to the baseband signal. So we can write omega I equal to the original carrier frequency plus a time varying quantity that is proportional to the message signal mt. This kf is called the frequency sensitivity. So this is the instantaneous frequency for FM. Now we know the relationship between phi and omega I. So we have to derive this phi I to represent the frequency modulated signal. So phi I equal to omega I dt. Omega I we have already said that it is the carrier frequency plus some time varying quantity proportional to the message signal. So put it here, that means omega c plus kf into mt dt, and that is equal to omega ct plus kf is a constant mt dt. So this is instantaneous phase. So SFM can be written as A cos omega ct plus kf integration mt dt. So this is the expression. Now we have to understand frequency deviation. The instantaneous frequency of FM signal varies with time around the carrier frequency omega c that we have seen already. This means that the instantaneous frequency of FM signal varies according to the modulating signal. The maximum change in instantaneous frequency from the average frequency omega c is called the frequency deviation. This maximum change in instantaneous frequency omega I from the average or the carrier frequency omega c depends upon the magnitude and sign of this kf and mt. So frequency deviation delta f can be written as in hertz. Equivalent form is delta omega, that can be written as kf mt max, kf into mt max. Now if we see the two signals, one is FM, another is PM. If you see these two signals, then you can see that their expressions are almost identical. The only thing is that in FM the baseband is applied with an integrator, and here we don't require any integrator, baseband is directly applied, and that makes it is difficult to distinguish between this FM and PM if we don't know anything about this MT. If MT is known, then only we can distinguish. Otherwise, it is very difficult for us to distinguish this FM and PM because they are almost identical to each other. So we can generate FM using a phase modulator, or we can generate PM using a frequency modulator. So MT, if we pass it through an integrator, and then if we use a phase modulator, carrier wave is there, then we should get FM. Similarly, the message signal, if it is passed through a differentiator, and then if we have frequency modulator, output will be a PM. So it is very difficult for us to identify this FM and PM, and also it is very easy to generate FM using a phase modulator or PM using a frequency modulator. Now we will try to understand the frequency modulation with the help of single tone system. Here MT can be written as Vm cos omega m t, and C equal to A cos omega c t. So St equal to A cos phi instantaneous phase. Now for Fm, omega I equal to omega c plus kf into Vm cos omega m t. So in this case, delta omega can be written as kf into Vm. So we can write omega I equal to omega c plus delta omega cos omega m t. So now we have to determine phi I, omega I dt, that is equal to omega ct plus delta omega by omega m sine of omega m t. Now we define modulation index MF equal to delta omega by omega m, that is equal to delta f by Fm in terms of linear frequency. That means phi I equal to omega ct plus mf sine omega m t. So St equal to A cos phi I means this one, omega ct plus mf sine omega m t. To understand this, let us see this figure. This is the carrier, this is the modulating signal. Next we have the amplitude modulator signal, then we have phase modulation system, and finally we have frequency modulation system, frequency modulated wave. And as you can see, this phase modulation and frequency modulation, it is very difficult to identify. only we can identify if we know the original message signal, otherwise it is difficult. Now depending on the value of delta omega or delta f, that is value of frequency deviation, or in other words, since frequency deviation is dependent on the frequency sensitivity kf, then based on the value of this kf, we have two type of FM. One is narrow band, another is wide band. Narrow band means small kf, and wide band means large kf. So let us try to understand narrowband FM first. We have already seen that the signal expression is like this: 2 pi fct plus mf sine 2 pi fmt. That can be written as a cos 2 pi fct into cos mf sine 2 pi fmt minus sine 2 pi fmt sine mf sine 2 pi fmt. Using the expression of cos A plus B. Now for narrowband FM, kf is small, kf is small, that implies that mf is small. That means mf much less than 1. So this is the condition. So under this condition, cos mf sine 2 pi fmt since mf is very small, we can write it as 1, and sine mf sine 2 pi fmt is nearly equal to mf sine 2 pi fmt approximately. So we can write st equal to a cos 2 pi fct minus mf a sine 2 pi fct into sine 2 pi fmt. So this is the expression for narrowband FM. Narrowband FM with MT as VM cos 2 pi fm t. Now this expression can be written in this way: st equal to not exactly equal to, we should write it as approximately, because it's approximate calculation. We have some approximations here. So a cos 2 pi fct plus mfa by 2 cos 2 pi fc plus fmt minus cos 2 pi fc plus is there, so fc minus fmt. This is for narrowband FM. Now if you can remember, st for am can also be written as a cos 2 pi fct plus ma by 2 cos 2 pi fc plus fmt plus cos 2 pi fc minus fmt. So it appears that narrowband FM and AM, their expressions are almost identical. So narrowband FM has got three components: one is the carrier, another is the upper sideband, and another is the lower sideband. So only two sidebands are there, and the narrowband FM expression is almost identical to that of the AM. But there is certain difference between these two signals. To identify this difference, we have to draw the phasor diagram. So first, let us try to understand the phasor diagram for AM. Phasor for AM. So to draw this AM, the carrier is taken as the reference. So this is the carrier. Next we have two sidebands of amplitude MA by 2 with frequency FC plus FM, and then another is the frequency FC minus FM, and FC is our reference. This one is our reference. So these two sidebands will be like this. So this one is the upper sideband, this one is the lower sideband, and the resultant of these two is this. So OA is the carrier, and this one is the, say, B. AB, this vector is the sideband, total sideband vector. Now what happens for narrowband FM? Here also we will take carrier as a reference. So carrier, the upper sideband is same as that of AM, same thing. The lower sideband for AM was in this direction, but for this case we have a negative sign. So instead of in this direction, it will be in the opposite direction. That means this is the lower sideband, this is upper sideband, this one is lower sideband. So the resultant of these two is the total sideband. So O A B, and this is the resultant FM. So as you can see that with in case of AM, the resultant of the two side frequency phasors are always in phase, with the carrier phasor. The effect is that the resultant phasor representing the AM wave has an amplitude significantly different from the carrier phasor amplitude and is always in phase with it. Whereas for this case, the carrier phasor and the FM, they are having some phase difference between them.